So now it'll turn the appropriate direction if there's an object there, and then we need to handle if there's not an object there. So we will say else no object present. We just want to give it a forward velocity. So we will say velocity message dot linear dot x, the only linear axis we actually have access to, equals 1.0. So let me double check what I've got going on here. Okay, and then the last thing we need to actually do is publish our message. So we are going to then, going back to our initialization function, we called our publisher self.velocity_publish. So we are going to call self.yell or pub dot publish underscore lowercase publish, and then we just pass it our velocity message, and that will then publish it to our topic, and the robot will then do it. Is everything clear so far? Yes. Okay. Okay. The last thing we're actually going to do here, in the interest of readability and sustainability, is we're actually not going to have this set to 1 and -1 because in this lab we do not like random magic number constants. So instead we're going to set some static variables that we're then going to have here. So so who does not know what a static variable is? Someone does not know what a static variable is. Okay, so don't shame him because then people don't ask questions. So so a static variable is a variable that, so a normal variable in any programming language is constrained by its scope. So if I have a function and I create a new variable in that function, and the function runs and then the function ends, all the variables in that function disappear. They go out of scope, right? Similarly, if you have a class and you have a member function of that class, you can access that function anywhere within your class, that instance of that class. But if you create one instance of the class and change that variable, and then create another instance, that new instance does not have access to the other class's variable, even though they're the same class, they're different instances. So static variables are variables that essentially have just global scope. And so that means in standard programming is if you have a static variable that you have inside a function, for example, every time you call that function, that variable is maintained. So you can have, for example, a static count variable that you increment every time you call a function, and it'll tell you every time you've run that function anywhere in your code. Similarly, in a class, if you have a static variable, that variable is the same across all instances of that class. And so you might be asking why this is relevant, and the reason is because Python does not actually have constant variables, which is kind of weird. But the convention that we typically use in the lab is that we use static variables for constants that are used within a class, because we don't need most of the features of static, but it essentially indicates that this is a property of the class as a whole and not of the particular instance we're using. It's not going to be changed, it just is there. So in this case, we're going to have two static variables we're going to define. One is going to be angular speed, which will be 1, and the other will be linear speed, which will also be 1. And so then we're going to have those, and we're going to replace those magic numbers in our code with our effectively constant values. And so for static variables in Python and similarly in other languages, you don't say, for example, self dot whatever. Instead, you use the name of the class when you're calling them. So our class name is navNode. So to call this static variable, we will say navNode dot angular speed, and that is that make sense to everybody? Does everyone kind of get it? And then similarly, over here, we're going to do -1 times nav node dot angular speed. And so the advantage of this, as opposed to just saying 1 or -1 or what have you, is now if I'm running this code and I decide, hey, I don't like the speed, I want to change it, rather than having to dig through the entire code to find where the numbers are and possibly missing some numbers, I can just go up here, say, okay, I'll change the angular speed, I'll change the linear speed. What's up?
Oh, don't worry about it.
Okay. And then down here we also need to change our linear speed like that. Okay, so that is what we have there. So now this is a completed ROS class. So now what we need to do is actually execute it in our code. So to do that, we're going to start off with this little line. I assume I'm not gonna ask. Some of you have not seen this before. This is kind of a pseudo version of main in compiled languages like C. What this does is it checks whether or not this module is actually being executed or not. So if you're running this file from the command line, it's going to see that this is true, and then anything you put under it is going to run. However, if you are just importing it into another file that you're then running, it's not actually being executed, but the code is being included. And so that means that anything in here is not going to actually run. And so this basically serves two purposes. One, it's just a convention because it kind of replaces the idea of main, so you can always know, okay, all the important executed code is going to be under this block. And two, it actually serves really important purposes for testing, because what you can do is if you have a class, right, it's not actually going to ever be executed, it's going to be imported into your other files. You can have a line like this that you can then put your test code into. So that way, you know, if you call it directly, it'll run your test code for you, and otherwise that code will never actually be run. So that's why you use this. So from under here is where we're actually going to put the code to run our node. And so the way we typically run it is like this. Copy this over real quick. Okay, so hopefully everyone's familiar with try except blocks, but if you're not, a try except statement is basically a way of the programmer can catch errors so that the code doesn't just break when you don't want it to, or so that you can define the way it handles the error yourself. And so the way it works is that anything you put in your try statement, the try colon and whatever else, is going to be executed like normal until something breaks. So if nothing breaks, it'll be executed and then we move on. If something breaks, then it stops execution and then the except block comes into play. So here it checks if the exception that is raised, it matches any of the exceptions you have called in your except statement, which in this case is only one, which is the ROS interrupt exception. If it is, then it will then save that exception to the variable you provide, which we called error, ERR, and then it will run whatever code you put in your except block. If there's an error that you don't explicitly catch, it's just still going to break. You can also choose to do except exception, which will catch every possible error, or just except, which will also catch any error. So in this case, we're only looking at one, which is the ROS interrupt exception, which essentially means if we Control-C, if we kill this program while it's trying to start up, then we will handle it. And so the way we handle it is with this line. So another thing about ROS is that print statements don't always work either. Again, it's a thing of if you're running it directly, like calling Python, whatever your file, print statements work fine. If you're running it through ROS, they don't always work. And so instead what we use is the ROS log. And that is called by using commands like this. So for example, rospy.log info in whatever string you want. That will then save that to the ROS log, which is a log of all the communications that are sent out by every node running at the same time, and it will also conveniently be printed to your terminal. So that's used a lot if you want to test. It's basically a print statement. It's just log info. So there are two similar commands, ROS log error and ROS log warning. Basically, the only difference is that they're categorized differently by the log system, and the color changes on the terminal. So we're using ROS log error, and we're converting our error message to a string, and then just forwarding that along to the log, so we have an actual log of it. And so then what we're doing is doing else, which some of you who know about try except might not know. Actually, there are 4 possible things you can put in your try except. There's try, except, else, and finally. And so the try except block runs, and then if there were no errors, else runs. And then regardless of whether there are errors or not, finally runs. So the point of else is that you can essentially encapsulate just the thing that has a chance of breaking in the try, and then everything else that you know is going to work in your else. And it's kind of just it's a convention, because that way you can easily look and see, okay, this is the part that we need to worry about, not all this other stuff that might or might not actually be a problem. So in our else, we're then going to say node.run. And that's it. Our node will now run, and it'll do the while loop forever until the node is killed by ROS. So that is a completed ROS node. Are there any questions thus far before we keep going? Anyone? I would really like some questions at this point, because I think people have to not understand everything. Okay, I guess assuming people understand everything, I am going to talk about some stuff before we move on that I did not include here, but that I think is important for people to know about when using ROS. So the first is the idea of waiting for a message. So a lot of the time people do, or will need to do in ROS, is particularly in navigation, they will have a topic they're subscribing to, and they need to get data from that topic before they start doing things, right? So for a big example of this is, say you're doing some mapping program. You have a robot, you're trying to make a map, and you need the odometry information from the robot to start making your map, because you need to know where it is. And so the problem that can arise is if you have your callback and you have your while loop that's running, if the while loop starts running before you get your first data, then your initial value for the location is going to be 0, right? And then when you actually start, it's going to jump off to some other place, and that'll completely screw up your map. So the solution that typically is done is people will say, okay, we'll have a flag in our callback that's set, like a first received message, being able to say received equals true. And then that way at the beginning of our while loop we can say wait until received equals true, and then we'll actually do our code, so that way that doesn't happen. Problem is that you are wasting clock cycles by having that little assignment of received equals true, which is not a big deal a lot of the time, but if you're running your callback 100 times a second, those clock cycles add up very, very, very quickly. And so the solution that ROS conveniently provides instead of that is this little thing called rospy.wait for message. What that does is you give it the name of the topic and you give it the message type, and then it'll just block until it gets a message from that topic. And so the way that you typically handle that is you have your callback set up, and then at the end of your initialization function, you just call this for whatever topic you need, odometry for example, and then it won't let you go on until it's done. And so that way your while loop is guaranteed to not actually execute until you get your initial data. So that's important. Another one that's important is on shutdown. So who has messed with exit hooks? Who knows what an exit hook is? Pretty sure you have. For socket service.
Yeah.
Okay. No one else has, so that's fine. So an exit hook or an exit handler is basically code that you register with your program to run before the program closes. And so this is typically used in serial communication, socket communication, anything where you're calling stuff that has to kind of open a connection, and that connection needs to be closed before you actually close out your program. Otherwise, you risk that connection staying open and then not being able to actually talk to it again and things like that. And so typically the way you handle that is Python has this nice @exit module you can import where you register a function with @exit, and then it'll be called when the program exits. However, ROS has its own thing, which you don't actually need to import. It's part of ROS Pi already, and it's called onShutdown. And it doesn't check for the explicit closing of the program. It checks for ROS itself shutting down, which is what you want usually. And so it works the same way. You have onShutdown, you pass it a function of your own making, and then when ROS shuts down, it'll call your function. So if you have a serial connection you have open, you can just call, you can have a cleanup function that closes your serial port, does everything, and give that to onShutdown, and that way you can be pretty much guaranteed that your serial port will be closed safely before code exits. And that's very, very important, especially for serial stuff, which is important for us because we use a lot of Arduinos, and you communicate with Arduinos over serial connection, so you need to know this. The other thing is, we talked about delay already. I think that's about it. Does anyone have any general questions about ROS, things that were unclear? Loud no, apparently. Okay, so in that case, we will move on to some other stuff. So we have now written our first program. So as I said, I'm going to use the GUI to navigate so you guys can see. Can everyone see this? Everyone good? Okay. So we're going to go to, so this is not the workspace we just created. This is the workspace I made the other day, but so far it's identical. And so now that we have this program, we want to have a way to actually launch our program. And so the way you do that is via a launch file. And so ROS has its own system called ROS Launch, which lets you create file definitions for a list of things you need to launch at the same time. Then you can just call the launch file and it'll launch all your programs for you. It'll launch other packages. It'll do all sorts of nice stuff so that you don't have to, go to the terminal and individually launch every single file. And so ROS Launch, just get into it. So why are we using ROS Launch when we only have one file? The answer is because you pretty much never have just one file. When you're working with robots, you will need to launch one of two things. You'll either need to launch a simulation to pretend it's a robot, so you'll need to have your program plus a simulation package that you're launching, or you'll need to launch the appropriate bring up files, bring up programs that your robot needs, because the way that ROS works is it's essentially an interpreter between your hardware and your actual programs. And so if you have a robot, for example, the Jaguar off in the corner there, it has a bunch of onboard embedded hardware, and that does stuff. It translates from velocity to motor driving. It translates sensors to actual output data, things of that nature, and then it takes that data and has a serial, whether Ethernet or some kind of connection, that sends it to your actual computer. And when it's on your actual computer, it's not in ROS. It's just on your computer in a serial port or Ethernet port or wherever it is. And so to get it into ROS, then there is a bring up file which launches a bunch of nodes that then convert the data back and forth for you. And the reason this is good is because it essentially creates a uniform, homogeneous interface that you can use regardless of the robot. So I was talking before about how typically for velocity, command velocity is the name of the topic, and for scans, scan or base scan is the name of the topic. The reason that's so is so I can write something like this we just wrote and plug it into one robot and have it run, or I can take it and plug in another robot and have it run exactly the same way, because all of the hardware specific things are happening in the bring up files and on the actual hardware itself, and my high level code is completely agnostic. So Yeah, that's why it's good. So anyway, that's why you typically are never going to have just one file that you're launching. So in this case, we're going to start out with a simulation. And the simulation we're going to be using is called Stage. Stage is a 2D simulator for ROS, and it's nice. You can draw maps and then have your robot run those maps. You can literally draw them in Paint. It's pretty neat. And so there's on the STARS wiki, there is a zip file that you can download. I think it's called Stage Example, and it has a bare bones package that you can put a launch file in it, I think called test.launch, and you can launch that and it'll pull up the stage window and it'll have a robot, and that's it. And so you can take that and then you can add your code to it, or your nodes to it, and add those to the launch file, and then you can immediately run your robot in the simulation. So I already have this pre-built, so we're going to go into it. This is the launch file that I wrote, so this probably looks weird, but I'm going to explain it. So a launch file uses tags like XML and other languages like that. So first of all, top level, you need launch tags that everything else goes into. That tells ROS it's a launch file, first of all. And then every node you want to launch is going to be called, you're going to need a tag that looks like this. I'll write it so it's a bit more clear down here. You need node, and then you need the package name. So in this case, if you look here, this is our package. I call it nav test, and then the type is the file itself. So ours is navnode .py, and then name is just the identifier you're giving it. Typically, it suffices just give it the same name as the file type, and then finally output. Just put screen. You can do other things, but 99% of the time it's going to just be screen. That's just telling you where the things from this file are saved. So if you have your ROS log, you can save it to a text file, for example, rather than having it up on the screen if you want to. But usually you want it on the screen. And then finally you need your closing slash, and that's how you load a file. And so then any nodes you have in your launch file will be brought up when you execute your launch file. So we have our node that we created, nav test. We also have this one here, which is our stage node that we're launching. So the package is called stage ROS. The type is stage ROS, the name is stage ROS, and then this argument parameter is where we're giving it a world file that it loads to actually create its map. And that respawn false, that you can actually put that in yours too. Basically, that just means it's default to false, but essentially it means if it dies, it's not going to try to start up again. So if you want it to try to start up again, you should set it to true. And then these, you don't really need to worry about these. These are remap tags, which are taking our topics that we defined and remapping them to be the appropriate topic names that stage expects. So rather than this long velocity thing, it just wants command velocity, aka the standard thing, and instead of scan, it wants base scan. So that's our launch file. Any questions about launch files? I believe this has gone over in the ROS tutorials. Correct me if I'm wrong, though. Yeah, so we have this file, and so let's say we want to actually launch some stuff. So, so there are two ways to run things in ROS. The first way is with ROS run, and the other way is with ROS launch. And so ROS run is the way that you can launch an individual file. And the advantage of ROS run is that you don't have to know where that file is, because as long as you have it, let me close out of this. Okay, that's cool. So as long as you know the package name for your files in, and you know, and ROS has its source into your current environment, you can just go to it. So in the tutorials, you know, you go over ROS CD to go to a directory. So, you know, if we're at home, I can say ROS CD and then go to nav test, and now it's taking me there. Similarly, if I want to run my nav node by itself, which I don't know why I would, but I can say ROS run, and then give it my package name, which is nav test, and then finally give it nav node, and it auto-completes because it knows where it is. And then I can press enter, and it'll run that file, just like a normal Python execution. Important to note that, as I think goes over in the tutorial, I'm sure it does, ROS core has to be running for you to do things in ROS, and ROS run does not auto-launch ROS core. So if you try to do ROS run before the core is running, you'll get an error. In contrast, ROS launch does auto-start ROS core, so you can do launch files without having to explicitly start ROS core. Another reason why ROS launch is nice. Good question?
No, I have a question about my computer.
Okay.
It's doing weird things.
I can't help you with that,
Yeah.
unfortunately. So, let's see here. So let's say we want to do our, is this clear to everybody? I mean, make sure I'm not skipping over steps that people might find confusing. So let's actually launch our little simulation then. Excuse me. So first of all, I need to source my previous workspace. Okay, and then I'm going to use ROS launch. So I'm going to say ROS launch, again, package name, and then the launch file. If you only have one, you can just press tab and it'll autofill it in because there's only one possibility. So I call it test.launch, and then I'm going to hit enter. And so it's starting up ROS core for me. It's taking a second. Okay. And so this is stage. So this is the map I created. This is all basically drawn in paint. It can be any arbitrary thing. It doesn't appear to be moving, which is interesting. One second. So okay, so now it's not moving, which means something has gone wrong somewhere. Oh, and let's see. So let's see what that might be. Oh, I know what it is. So in our launch file, I was renaming scan to base scan, but interestingly, I actually need to do base scan to scan because it is in fact the laser is coming from the simulation, not from my node, and so I need to change it on the simulation side, which is the from side. So it's not doing anything because it's not actually receiving any laser data. While we're here, though, other things happening, let's actually try seeing some stuff. So let's say we want to know some stuff about what's happening right now. So we have this up. So first of all, let's see, we want to know what topics there are. So we can do ROS topic list, and that gives us a list of all the topics that are currently being published or listened on. So we have base post ground truth, which is a simulation thing, base scan, which is the scan data coming from the simulation. We have clock, which is just a clock tick that used to synchronize things. Command velocity, which is where we're publishing our velocity data, or rather, it's not publishing in the right place either. Interesting. We'll deal with that in a second. So we have odometry, which is the odometry from the robot, and then we have scan, which is where we're trying to listen for laser data, but we aren't finding it because it's not being published there. So for example, if we want to see our laser scan data, we can say ROS topic echo, and then base scan, and that's the output we get. So it's publishing laser scan data very, 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 very quickly. And so we're going to kill that. And so that's what we get is an array of intensities and then an array of distances from the scanner where it's detecting things, and as well as our constants that we defined earlier. So we can see that's clearly working. That's clearly publishing things. And then let's say we want to Let's see odometry. We can do a similar thing. Also echo odom, and again we're getting odometry messages. The robot hasn't moved, so it's just sitting in place. So this is an odometry message for reference. It has position and orientation, essentially your XYZ coordinate in space as well as your angle. Yep, that's odometry. It's 0 because there's nothing happening. We're not moving. So what we're going to do is go back and we'll kill our program, and we'll try again now that we've changed our parameter to the new things. So we can try again, finish the launch, and again we have no movement. So clearly something has gone wrong somewhere. So if we list again, still have 2 scan things. Okay. So in theory this should work. Instead, I'm going to just change it in here because I'm not going to keep you guys waiting while I try to debug my ROS code. So we're going to comment out this line, and we're going to replace this long thing with just command velocity, and then similarly for our subscriber, we're going to comment it out, and we're going to replace it with base scan, and then in our launch file we're going to just delete these remap things because they're not apparently working with them. Okay, so now we hopefully have fixed it. Let's try one last time. And there we go. So now we have a robot, and it's moving forward. It sees no obstacles. It sees an obstacle, turns. Can people see this robot? It's really small. You might not even be able to see it. Let me zoom in. I can't zoom in. I can. Okay. So there we go. There we go. There's our robot. And so you can see actually the laser scanner. It's very faint, so you might not be able to see it, but that's the laser scan data that it's actually outputting. And so you can kind of see it chugging along there. And so this is just an obstacle that we defined, so you can actually move this around. The other things are like walls, you can't move them, but you can actually kind of crawl your robot with this obstacle if you want to. Okay. So, yep, so that's a simulation. Again, and this is just some output data I defined, so it's giving me the count of the things it's seeing. Oh, and it just found an obstacle, so the count is high and it's low again, like that. So that's how you get a robot working simulation. That took like an hour. So the last thing I'm going to talk about before we actually move to a real robot, which I imagine is going to be more interesting, is sensors. So this is a laser scanner. This is a Hokuyo 3-meter laser scanner. So this is a big thing for us because this is basically exactly what we're using the simulation, except now it's real. So this is plugged in to my computer, and the nice thing about ROS is that there are drivers for everything already. So you don't have to spend all day trying to convert laser data from serial to a ROS message because someone conveniently made it for you. So, for example, to launch this guy, I have downloaded a package called Hokuyo Node, which is the brand of this laser. And so I'm going to do ROS launch, Hokuyo Node, and then let's see what the possible options are. I want to do Hokuyo test. Oh, I stole that. That's why. Hokuyo test launch. Okay. And so I'm going to run that, and again, this is all predefined. I did not make any of this. So it creates the nodes, and now it is streaming laser data. So I can now go over here and list. Now there is there's a scan thing running. I can again echo scan, and now I see laser data again, but it's different laser data because this is actually from a real sensor, and I can change it by moving it. So now you have this, you know that the sensor's working, so now you want to actually see what it looks like. You want to make sure that it's working correctly, what have you. So there's a nice visualization tool built into ROS called RViz, which lets you do really neat things. And again, this is built into ROS. You don't have to download anything. You can launch it on your computer right now. There's not anything to see, but you can do it. I have something to see, which is a laser scanner, so we're going to pull it up. So that's going to be ROS run, then RViz, and then RViz again. So package RViz, file name RViz. We're going to pull it up and see some stuff. So this is what RViz looks like. It's like a simulator, basically. And once we're in here, we can add observation sources. So we're going to click add, and then we're going to scroll down to the laser scan. And then now we have this new laser scan property, and we're going to go to topic and enter scan, because that's the name of our topic. Hit enter. And now, you guys probably can't see that very well, but let's see. Oh, okay, so now this is the real-time data the laser is seeing. So I can put it up here. This is not a good place to do this, apparently.
It'll be more visible if you change the point size.
Oh, yes. Yep.
So the size under laser scan.
Oh,
Because right now it's 0.01.
So we have a 0.1. There we go, that's better. That's more visible. There's not a lot of good walls to see around here. Yeah, so you can actually see there's a computer kind of inset, and then you can, this is a laser scanner. So yeah, if you have a sensor, or you have a you can also work with the robot, so you can visualize odometry data, anything you want. You can pull up an RViz and get a real nice look at what it's actually doing. This works with all sorts of nice stuff. Yeah, so that's RViz. So let's kill that. Okay, so now we're going to actually go to a real robot, and to kind of try to prove the point that this actually, there's a reason for all of this. All we have to do to get to a real robot is switch around some comments. So we're going to just uncomment those lines we had earlier with the different topic names, and we're done. Now this works in a real robot. So let's get into robot. So I regret that this is going to be less visual for y'all, because I'm going to have to unplug this in a second from the HDMI cable for it to actually drive, but it should still work. Let's go ahead and turn off the camera and the mic, because it's not actually going to get anything else useful, because I'm going to be all over the place now.